A login system may seem trivial. You type your email, your password, and that's it. But behind that single click, there is a much more complex process. Your request travels to the server, retrieves the password hash, and then runs a hashing algorithm, one that is intentionally designed to be slow and resistant to attacks. All of this happens in milliseconds, so fast that you hardly notice. But now, imagine thousands of people from all over the world trying to access at the same time. Suddenly, those calculations become a monumental bottleneck. The challenge here is clear. How do we take an ordinary login and scale it to handle thousands of requests per second? Today, we are going to push that limit to see how far can we go. Let's start with the simplest possible implementation of a login function. First, we try to find the user in the database by their email. If the user doesn't exist, we immediately throw an error. Next, we compare the provided password with the stored password hash in the database. If they don't match, again, we throw another error. But if everything looks good, we create a JSON web token that contains the user's ID and email, so the system knows who you are in the next requests. Finally, we return the result that contains the user's ID, their email, and the signed token. Let's now test some requests in Postman. The setup is simple. The URL is localhost 3000, which is the port where my Express server is running, and /login, the route I defined to handle logins. Now, let's add the body params, email and password. If I hit send with body credentials, the server responds with a 200 OK status code, returning the using information and a JSON web token that we could use for further authenticated requests. But if instead I type wrong credentials, it correctly returns a 401 unauthorized error. So far, everything looks good. Let's take a quick look at the latency of these manual requests. We are seeing values around 70 to 90 milliseconds on average. That's a solid response time. Keep in mind that I'm running this on localhost, so there is almost no network latency. In a real deployment, depending on the server's location, you might easily add another 100 to 200 milliseconds per request. Now, let's put some real stress into the system. For that, I will use a tool called Autocannon. It lets quickly simulate high concurrency by firing many requests in parallel. As a first test, let's run 50 concurrent users for 10 seconds and see what happens. Okay, so the simulation is over and we can see some useful information. The first value to highlight is the average latency, which is 2 seconds. On average, each login request took almost 2 seconds to complete, and 2 seconds is an eternity for something as simple as logging in. The P50 or median sits at 1.9 seconds. In other words, half of all requests were slower than that. Looking further up the table, the P97 and P99 percentiles reach 7.5 to 8.8 seconds. That means the slowest users were forced to wait almost 10 seconds just to log in. While the maximum observed latency was almost 10 seconds, the real issue here is not the peak, it's that the majority of users are already above acceptable thresholds. To put this in perspective, in a real production system, any login taking more than 1 second already feels slow. Here, with only 50 concurrent users, the server is almost saturated. This is the clear sign that the current implementation is not enough for handling this amount of traffic. In order to identify possible bottlenecks within our API, we're going to use OpenTelemetry. OpenTelemetry is an open source standard for collecting telemetry data from system, things like logs, metrics, and traces. It helps to understand how a request flows through the application and where time is being spent. In other words, it gives us X-ray vision into our backend. Back in our code, let's create a new file to initialize the Node.js SDK for OpenTelemetry. Here, we specify a sampler, in this case, the always-on sampler, which captures every single request so we don't miss any details. We also configure the exporter, which defines where the traces will be sent, and enables some built-in instrumentations. These instrumentations automatically record data such as the HTTP method, root access, client IP, content length, and even Postgres query execution times through the BG instrumentation. But instrumentation alone isn't enough. We also want to trace our own business logic. In the login process, there are two critical operations. Find user by email, which queries the database to verify whether the email exists, and check password hash, which compares the user's password against the stored hash. For find user by email, we create a span and add useful context as attributes, for example, the user email. Once the creator finishes, we close the span. For check password hash, we also set a span named check password hash, and if the comparison fails or an exception occurs, we record the error inside the span before closing it. OpenTelemetry captures all of this, but in order to see it, we need a visualization tool. There are several options in the market like Grafana, Datadog, or Honeycomb. In this case, I will be using SigNoz, which is open source, easy to deploy locally, and provides a very friendly UI for exploring traces. Once the dashboard is running, all we need to do is restart our API server. From that point on, OpenTelemetry starts recording and exporting data automatically. Let's make a single login request in Postman, and then refresh our SigNoz dashboard. We immediately see new traces being recorded. If we open one trace, we can follow the entire journey of the request, from the express route receiving the HTTP call to our custom functions, and finally back to the client response. Looking at the details, this particular login request took about 73 milliseconds end to end. Database lookup in find user by email only 1 millisecond, with the connection and query together totaling about 1 millisecond. And lastly, we have the check password hash function that alone takes the majority of the time of the request with 71 milliseconds. Now that we have tracing in place, let's put our system under stress again. Now, I will run Autocannon again with 50 concurrent users for 10 seconds, and then inspect the traces in SigNoz. Here we are at the SigNoz panel. Once I refresh the dashboard, I can see a list of all the required traces. Let's filter by spam. I will start by looking at find user by email, and then order by duration in ascending order to get those queries that took less time to execute. And as you can see, most of these spans complete in under 1 millisecond. If I click into one of the early traces, the total request took just 66 milliseconds, with almost all of the time, 65, spent in check password hash. Database connection and query execution together is barely 1 millisecond. So at first glance, the biggest cause is clearly password hashing. But let's look at requests that were handled while the system was already saturated. Now I will sort by duration in the same order. On later traces, I start to see values with more than 3 seconds. Opening one of these traces shows a completely different picture. Now find user by email appears to dominate, consuming almost 3 seconds, while check password hash only accounts for about 450 milliseconds. So what's happening here? Is the bottleneck the database, the compare function, or both? To find out, I will query BG status statements inside Postgres. This catalog view shows the real execution metrics of queries, so we can know how much time they took to execute. For our email lookup query, the stats tell me that it's been executed with an average duration of just 0.028 milliseconds, and most importantly, the maximum recorded execution time for this type of query is only 4.22 milliseconds. That is far away from the 3000 milliseconds that SigNoz was showing. That means Postgres is actually lightning fast, so why do our traces show multi-second spans on find user by email? The reason is Node.js event loop. When the system is under heavy load, intensive tasks like bigquery password comparisons take over the event loop. While that comparison is running, everything else, including database queries, has to wait its turn. From the trace, it looks like the database was slow, but in reality, Postgres had the result ready almost instantly. It was just blocked from sending it back. And here's the key lesson. If you only look at the traces, you might blame the wrong component. That's why combining tracing with real database metrics is so powerful. So under high concurrency, the true bottleneck in our system isn't Postgres, it's the check password hash function. Now let's take a closer look at the check password hash function to understand what's going on. This function simply calls the compare method from the bcrypt model and returns whether the passwords match. But if we scroll up to the import statement, we notice something important. The model in use is bcrypt.js. Let's check it on npm for more details. It turns out that bcrypt.js is a pure JavaScript implementation. That means everything is executed on a single Node.js event loop. And according to the documentation, it's about 30% slower compared to the native C++ bindings. So let's swap it out and use the native bcrypt implementation instead. Let's put this new implementation under load to see if there is a substantial difference. We will simulate 50 concurrent users over 10 seconds and observe the results as we did with the old implementation. This time, the average latency drops to around 800 milliseconds compared to the 2 seconds we saw with bcrypt.js. That's more than 1 second improvement in average with a single change. But why does this swap make such a difference? The answer lies in how bcrypt works under the hood. When you run in pure JavaScript, every expensive cryptographic operation blocks the event loop, preventing Node.js from handling other requests. By contrast, the native C++ bindings offload the heavy computation to the thread pool, freeing up the event loop to continue serving new requests in parallel. This architectural difference is what gives us such a dramatic performance gain. Let's push it further. This time, let's try with 100 concurrent users. Now, the average latency has jumped another 700 milliseconds, crossing the 1.5 second mark. Let's now try scaling up to 200 users. Here, the server still holds, but the averages are back near to 2.8 seconds, dangerously close to the levels that we initially had with bcrypt.js. This experiment shows that while switching to native bcrypt buys us some performance, our current architecture will quickly collapse under higher traffic. At this point, we have squeezed as much performance as we can out of software optimizations. But even with native bindings, bcrypt is still a CPU-intensive operation, and running it inside the same process as our API creates contention. So how do we break this limit? The answer isn't in tweaking more code, but in rethinking our architecture. Instead of asking our API to do everything, handle HTTP requests, talk to the database, and crunch through expensive password hashes, we can offload the hashing step to a dedicated service. This service has a single job: process hashes as fast as possible. Our API will simply send the request via an RPC protocol, wait for the result, and continue its flow. This separation allows us to scale the hashing layer independently. If tomorrow we need to handle 10 times more logins, we just add more hashing workers without touching the rest of the system. To connect our API with the hashing service, we are going to use a protocol called gRPC. gRPC is a high-performance, open-source RPC framework developed by Google. It allows services to communicate with each other directly, using strongly typed contracts defined in a protofile. Instead of changing plain JSON over HTTP, gRPC uses protocol buffers, a compact binary format, making communication much faster and more efficient. The first step is to define the contract within a protofile. This file defines the contract between the client and the server. We have a hasher service with a single procedure called compare to validate a plain password against a stored hash. The procedure uses messages that act as strongly typed requests and responses. For example, compare request has two strings, the plain password and the stored hash, and it returns a compare response with a single boolean field, match. That's all it takes to define the entire service interface. Now let's look at the gRPC server implementation. Load package definition loads the definitions from our protofile and gives us access to the RPC procedures that we defined. The compare function then calls bcrypt compare under the hood, the same optimized native implementation we already used in our previous step. Finally, we attach the compare procedure to a gRPC server, bind it to the default gRPC port, and start the server. At this point, our dedicated hashing service is ready to receive requests from the API. Now, let's take a look at the high-level design of the new architecture. The API still receives the login request and fetches the store hash from the database. But instead of doing the hashing itself, it sends the plain password and hash or gRPC to the hashing layer. This layer isn't just a single machine anymore. It's a pool of dedicated hashing instances, all orchestrated by Kubernetes. Kubernetes manages how many workers are running at any time, scaling them up or down depending on the load. I've already deployed this system using DigitalOcean's cloud infrastructure, orchestrated with Kubernetes. If you're interested in how I set up the full architecture step by step, let me know in the comments below. I will make a separate video covering all the details. The hashing component is the slowest and most critical part in the system. To give us a running start and avoid a cold start bottleneck, I have already scaled hasher service up to 8 replicas. I will run Autocannon from a dedicated virtual machine in the same DigitalOcean region as this Kubernetes cluster. This removes all that transatlantic latency so we can measure the true server-side performance. Let's try at first with 200 concurrent users as we did with the old implementation. We can see a significant improvement in performance compared in the previous version. The average latency is now only 248 milliseconds compared to the 2.8 seconds in the old version. The maximum response time observed for any user request is just 1.1 seconds compared to 3.5 seconds that we previously had in the old implementation. In addition, the new architecture is now capable of handling an average of 202 requests per second, a substantial increase in throughput compared to the 59 requests that we had with the old implementation. That's almost 14 times more. Let's now take a look at the traces from the latest experiment in SigNoz. If we click into one of the traces, we can clearly observe the bottleneck is now located in the check password hash function and not in the database. If we inspect any of the traces, it looks like most of the request time is dominated by this operation. To confirm this, let's filter the traces and look for check user by email spans that look longer than 60 milliseconds. And as expected, we get 0 results. This strongly indicates that if our average request latency is 2 seconds, the vast majority of that time is being spent inside the check password hash. So our new architecture is working as expected. Now it's time to find the breaking point. I'm going to execute a series of incremental load tests pushing our system past its limits. Our goal is to identify the saturation threshold, that point where the average latency consistently exceeds 2.5 seconds, which we will define as an acceptable response time for a production login. After running the tests, here are the results that we've got. With 500 concurrent users, the system effortlessly sustained an average of 857 requests per second, with a fantastic average latency of just 577 milliseconds. The maximum latency was 2.6 seconds, and in overall, these are extremely strong numbers. It proves that our current deployment is more than capable of handling 500 concurrent users per second. With the double of users, we see the system delivers 728 requests per second, but the average latency starts struggling, more than doubling to 1.3 seconds. This is still well within our acceptable 2.5 second threshold. Crucially, the system remains stable with 0 timeouts. While the P99 latency did hit 4 seconds for 1% of users, the architecture managed the heavy queue without failure. Increasing the load to 1500 concurrent users, we've got similar results, with the average latency creeping up by another 200 milliseconds. This increase is totally expected and demonstrates predictable queuing as we approach saturation. Finally, let's look at the absolute limit, 3000 concurrent users. At this peak, the system managed an impressive 1100 requests per second, but the average latency hit almost 2.5 seconds, right at our limit. The stress was clear. The P99 latency is nearly 9 seconds, and we started seeing more than 100 timeouts. This is our saturation threshold, is the point where our system's queuing can no longer handle the sustained load, and the response times becomes unacceptable for production use. If we were to be highly strict with our service level objectives and define our average acceptable latency at 1.5 seconds, our current infrastructure could comfortably handle about 1500 concurrent users. That is an incredible high throughput for an authentication system where the hosting operation is computationally intensive. To truly put these numbers in perspective, let's translate our RPS to a monthly user capacity. The current infrastructure under 1500 concurrent users sustain a throughput of 728 requests per second for the login operation. Let's do the math. 728 requests per second translates to 62.9 authentications per day, which means 1.8 billion authentications per month. This means that theoretically, this infrastructure setup could handle a volume equivalent to 1.8 billion active users if each user logged in once a month. Which companies operate at this scale? We're talking about the top tier of global technology: Facebook, Instagram, YouTube, or major e-commerce platforms like Amazon during Black Friday. While these companies handle an exponentially more complex domain logic involving hundreds of microservices and consulting different data stores, the login process remains a high-volume operation. The operation that demands the longest CPU time, the single most expensive step in the entire authentication flow, is almost always the hashing function. By successfully scaling the most CPU-intensive operation of the service over 1100 requests per second, we have demonstrated that this architecture is capable of handling the sheer volume of requests seen by these massive global enterprises, proving the power of horizontal scaling on Kubernetes. Thank you so much for watching. If you'd like me to do a complete deep dive video on how I deploy this entire infrastructure on Kubernetes using a cloud provider like Amazon Web Services or DigitalOcean, please drop a comment below. I will make a separate video covering all the details. Thank you so much for watching and see you in the next video.